One of the most common terms you hear kicked around when people talk about radioactivity is half-life. All radioactive isotopes have a half-life, and we typically use the symbol lowercase t 1/2 to talk about half-life, or to represent it anyway. So what the half-life is it's talking about the amount of time that it is taken for half of our initial amount of whatever we have to undergo radioactive decay. And half-life actually isn't just used for radioactive decay. It's talked about, you can use this term for lots and lots of different things. It's referring to a very specific kinetic, which means over time, reaction where when you start with a certain amount of something, it's going to decay at a very predictable rate that looks kind of like this. So the amount is on the y-axis and the time is on the x-axis. And if we talk about the half-life, if this is our starting amount, then half of that would be about here, right? So that means that the amount of time that it would take would be this amount of time. That would be 1 half-life. And then if this is our new starting amount, then we would lose half of it again. That would get us to this amount of time. So this would be another half-life, and they should be the same amount. And then we could go to yet another half-life. And this would be 3 half-lives. And you can see that it's going to get harder and harder for me to draw as we get closer and closer to that 0 on the y-axis. But the amount of time each time is going to go down at a consistent rate. So this is a very specific reaction. These are called first-order kinetics, and we'll learn more about kinetics later. But I'm going to mention it just so that it sounds familiar a little bit later. So each isotope has its own half-life. Some of them are extremely short, less than a second or even a picosecond, and others are extremely long. They could be millions of years long. So if, for example, we look at U-238, I think we might have mentioned this one before in terms of its half-life. I mean, I know I've mentioned the element. I like to use web elements, although they aren't comprehensive with every single radioactive isotope ever. They do have lots of them. So here is U-238. It has a half-life of 4.46 times 10 to the 9 years. So let's go ahead and write that out. 4.46 times 10 to the 9 years. So if we write that out with zeros, there's 6 zeros, and then we have, there's our 9 zeros. So this is 1,000, million, billion. Am I doing that right? Yeah. So these are billions of years, right? U-238 has a very long half-life, which means that there's still some present. So if something has a pretty short half-life, so this U-238, presumably if this is in the 4.5-ish billion years range, then this U-238 has been here since the Earth was created. So we can use the amount of uranium in rocks, also compared to its decomposition products, to estimate how old rocks are. So when we look at different isotopes, we know that some of them are super long, and then others are super short. Many of the man-made elements, especially the very large ones on the very bottom of the periodic table, those ones have very, very short half-lives. For example, most of the newest elements were only around for a few microseconds before they decomposed into something, like oganesson, for example, and tennessine. So let's talk about some of our elements, or excuse me, our radioactive isotopes that maybe have a slightly longer half-life, and we can kind of see an illustration of what this looks like. So let's think about iodine-131. This is a radioactive isotope. It's actually used to treat cancer in the thyroid, and this is because iodine is concentrated in the thyroid, and so if you treat it with this iodine-131, which is a radioactive isotope, the body will naturally concentrate the iodine in the thyroid where it can presumably kill the cancerous tissue and not be terribly problematic in other places around your body. So let's look at that balanced nuclear equation here for a second. So iodine is element 53, and this is iodine-131. It decays by beta emission, so that's an electron. So that means it's what's left still has a mass number of 131, but it will have the atomic number of 54. So if you check your periodic table, you'll notice that this is the element xenon. And xenon, this is a stable isotope. It's not radioactive, this xenon-131. And not only that, it's a noble gas, so it's not reactive either. So once this iodine-131 decays inside the body, it produces a harmless, unreactive material that's not going to do anything in your body. Iodine-131 has a half-life of 8.040 days. So let's just look at what our numbers would be like if we were talking about this chart right here. So let's say we had 1,000 iodine-131s when we started. Then after 8 days, so here's 8 days, we would have 500. And then after another 8 days, so now we're up to 16 days, we would have 250. And then after another 8 days, 24 days total, we would have 125, and so on and so forth. So you can see that pretty soon there aren't very many of these radioactive isotopes left. They fall off pretty quickly. And generally speaking, after about 10 half-lives, the radioactive isotope is assumed to be at background level. It's basically, it's gone enough, right? It's not going to be above background. So what this means is that if you have 10 half-lives, for iodine-131, that would be 80 days. So this is long enough that if you had, some radioactive iodine in your body and it was concentrated in your thyroid and it wasn't for medical reasons, it could potentially cause some trouble, but it would also be gone in less than 3 months. And it would form, something that doesn't really matter to anybody. So let's look at some additional radioactive isotope half-lives here. You've probably heard about radiocarbon dating. And radiocarbon dating uses carbon-14. Carbon-14 has a half-life of 3715 years, so that's pretty long. And it gets formed constantly in the upper atmosphere, where in the atmosphere you have some cosmic rays, which include neutrons, high-energy neutrons, that are hitting nitrogen. Not nitrogen 15, but nitrogen 14. And I actually didn't look at the whole process for this. So it's obviously not happening in one step because that would make radioactive nitrogen 15. So maybe we can figure this out. Carbon is normally present as two stable isotopes, carbon-12 and carbon-13, but some radioactive carbon-14 is made in the upper atmosphere, where you have cosmic rays apparently triggering some reaction with nitrogen to produce some carbon-13, or excuse me, carbon-14. And so that means that we have a regular supply of a tiny amount of carbon-14. And living organisms are taking in carbon all the time. You know, all of our food is carbon-based, our bodies are carbon-based, and so we are taking in, we're eating and drinking carbon-containing things, and we are exhaling carbon dioxide, and of course, you know, lots of other waste products that are going to involve carbon. So as a result, living organisms, because they're constantly taking in some trace carbon-14, they all have about the same amount of carbon-14. So they have a reliable ratio of carbon-14 to carbon-13, or you can compare it to carbon-12 inside their bodies. But as soon as that organism dies, it stops taking in new carbon. So after death, any organism is going to start decreasing in its carbon-14 concentration. This obviously isn't going to help the guys on CSI figure out what happened last week, but when we're talking about things that happened hundreds or thousands or 10,000s of years ago, we can use carbon-14 to carbon-13 or carbon-12 ratios to figure out about how long it's been. So notice that the half-life of carbon-14 is over 5,000 years, and the limit for doing carbon dating is about 60,000 years, or maybe a little less than that, which lines up pretty well with 5,700 years times 10, right? That would be 57,000. So you can see that after 10 half-lives of this carbon, we're no longer able to use it for carbon dating because there's not a significant enough amount of it left. So we do have some limits on it, but otherwise it's a very useful thing for looking at things that are older than 100 or so years, but younger than 60,000 years. So I mentioned first order kinetics earlier, and I mentioned this little graph, and there's actually some mathematical equations that we can use to predict how much of something is left over that has first order kinetics. So we said that the half-life is a number, but it also relates to how fast this reaction goes. And it turns out that it is equal to natural log of 2 over this number that is called the rate constant. And the rate constant has to do, naturally enough, with how fast these decompositions happen. So that means that we could rearrange this equation and say k is equal to natural log of 2 over the half-life. Because most of the time we have these half-lives, or we can look them up in tables. So we can get these values for the rate constant. And the other equation that we use here is one with some natural logs. I'm going to write it out, and then I'll tell you what all of the numbers are, and we'll do a practice problem. So this is natural log, and this x in brackets with a little bubble down at the bottom, this is the initial concentration of whatever the thing is that we're interested in. T is the time. Notice this does not have a little 1/2, so this is not the half-life. This is the time right now, whatever time we want it to be. Here's our rate constant again. And then this is the concentration now at whatever time. So I'll just put at time t. So let's see how we could use these equations to look at another very common radioactive isotope. So, for example, radioactive cesium, cesium-137 in this case, is a very common fission product of U-235 in nuclear reactors and in nuclear bombs. And notice what kind of an element cesium is. What column is it in the periodic table? Go take a look. Yeah, it's in the first column of the periodic table. So this is an alkali metal, and that means that it is soluble with a lot of things. So they mostly make soluble, water-soluble compounds. So this is problematic for radioactive isotopes because it means that it's going to be really super easy for these to dissolve if they're left out, where they can encounter water. So let's take a look at what its details are. It has a half-life of a little over 30 years, 30.2 years. So let's take a look at, think about some numbers. If we go back to the first nuclear bomb, which was detonated in New Mexico at the Trinity site on July 16th of 1945, that's a little over 75 years ago. Let's call it about 75 1/3 years ago. So let's imagine that maybe there were 100 cesium-137 atoms created. How many would be left now? Let's set this up with the equation so that way we can just kind of see this as an illustration of how to use the equation. So I said first that we can use the half-life to calculate the rate constant. So let's do that first. The rate constant equation using the half-life gives us natural log of 2 over t1/2. So natural log of 2 over 30.2 years. These are going to have kind of awkward units, so just don't worry. So if we do that, it's going to be 0.02295. I'm just going to keep a bunch of significant digits for right now, and then we'll round off later. And the units are 1 over year. So remember, K is a rate constant, so this is kind of like a frequency. So we expect it to be a certain number per time, which is what it is. We could convert this into some other unit, but it really doesn't matter. We're going to keep all of our units in years for now, so they will all work out. All right, so we asked how much stuff we have now. So this 100 is going to be our initial concentration. So that was X sub 0. And we want to know the current concentration. So our equation gives us the natural log of this concentration. It was minus KT plus natural log of X sub 0. So our K is 0.02295, 1 over years. And the time we said was about 75 1/3 years. And then we have plus natural log, and we said our initial concentration was just going to be 100. So go ahead and pause the video for a moment and solve this and see what you get. When I did this, I got 2.876. Actually, I had to do it a couple of times. For some reason, my calculator didn't want to keep the negative sign when I typed it in. So in order to undo the natural log, we're going to take both sides to the exponential function. So this will undo those ones, and then we'll have x is equal to e to the 2.876. So if I plug that in, I'm going to get 17.7 something, but I can't have a fraction of an atom, so I'm just going to say that this is about 18 atoms of cesium-137 that are left. So please do remember to do that. Just round to the nearest whole atom. If we're talking about whole atoms. If we're just talking about percentages or something like that, then you could keep 17.7, whatever. But since I started with 100 actual atoms, we were going to round that. So what you should have seen from this video is that we have the half-life, that this is the amount of time it takes for half of our material to go away, and that these half-lives can vary quite a bit, that some things have very short half-lives, in which case they probably are not going to stick around long enough to cause a lot of trouble for us. Some things have extremely long half-lives, like uranium-238, and mostly it doesn't cause us any trouble either because it's decaying so slowly that even if you're hanging out with a chunk of uranium, it's probably not going to irradiate you enough for you to worry about it. Especially if you normally do things like climb mountains where the elevation is high and you are exposing yourself to more radiation from space, or if you fly in airplanes or anything like that. So the main radioactive isotopes that are problematic in terms of the environment is mostly these mid-range radioactive isotopes. So isotopes with medium long, or somewhat longer but not super long half-lives do tend to stick around long enough that there's still a decent number of them left even after, say, 75 years. So 18 atoms left doesn't sound like a huge amount, but that's still almost 20% of the sample after 75 years. And 75 years is about as long as most people will live. So, this isotope is not going away during someone's lifetime. So any kind of radioactive isotopes that do have those kind of medium-long half-lives could be problematic if they can get out into the environment, which is why we need to make sure that we have things under control. All right. On the next one, we will actually talk about using radiation units and how they are measured and how they are tracked.